everybody to this new lecture. Now we are starting our second part of the lecture, which is about now dynamic processes, and we will mainly cover in this section stochastic processes and dynamical systems. And inside dynamical systems we will discuss mostly ordinary differential equations, but then also we'll have a little sidestep to partial differential equations, especially reaction diffusion equations. But today we start the whole new part with an introduction to stochastic processes. For this we need for a moment to go a little bit to probability theory. So if you have no proper background in probability theory, you should look up certain things. I will mention that in a moment. So what is the basic setting of probability theory? We introduce a set omega. This we will call the sampling space in our context. And so I will give you an interpretation of this with respect to our black box model in a moment. So, but you can already, it's a very good idea just to associate omega already with something that we can observe. And we have now to measure certain things inside omega. For mathematical modeling reasons, what do we want to observe in our black box? That's the question here. So whereas in part one, where we looked at structural models, where we mostly looked at system components and their connections or relations, to say that in a better way. So, looking at the pure structure of a model and the corresponding structure we hopefully see in the real world. Now what we measure is something different. We measure mainly events when it comes to dynamical processes. Dynamical processes will try to manage to model event sequences. But of course, there is this big distinction between discrete mathematics and continuous mathematics. In discrete mathematics, if you look at dynamic theories, single events will be just single points in time of observations where something happens. And if you look at continuous processes, then we will look at events per time period, and then of course this becomes a rate, and so differential equations are based on rates. And this is, if you interpret that from an observation point of view, it will mean that instead of having discrete events, you have a continuous event, so you just think something is happening all the time. Now, having discussed that space omega, the sampling space, we have now to look at subspaces, so subsets of omega, which can be observed. So maybe there's a whole mathematical theory that is based on that, and that is the theory of integration. So you want to measure certain things in omega, which means you have to dissect omega into certain parts where you can measure something. And here, of course, we use the Lebesgue measures, which is later then giving rise to the Lebesgue integral. And the Lebesgue measure defines implicitly, sets that have a measure which is zero. So that means you cannot measure anything inside. And measures that are bigger than zero, so that are positive. And all of these sets that are defined, on which you can define Lebesgue measures, These are called the sigma algebra A. So it's a family of subsets of omega, and this we call the sigma algebra curly A. Now the interesting thing for us is that each element of this family of subsets of omega will be called an event. So you know an event can therefore also be something that, for example, takes place simultaneously at different areas or coordinates of omega, or whatever you want to call it. So every element in this sigma algebra A is called an event. The last thing is we will now go to probability theory. So we don't take just any Lebesgue measure. We take a very special Lebesgue measure, which we call a probability. And so the probability will be defined as something that is defined on each element of the sigma algebra A into the interval 0, 1. So this gives a clear interpretation. You know, the probability, if something has probability 0, then it's never taking place. If the probability is 1, then that is an event that is taking place for sure. Okay, now we can define a probability space. So the triple omega, the sigma algebra curly A, and this probability P, this triple together is called a probability space, and P is called a probability. Now, because here we are doing mathematical modeling, it's of course very important to have a good feeling and a good interpretation for probabilities. So, you know, we cannot afford here the luxury just to make that completely abstract. Abstraction has, serves a good purpose, because then you can just do the maths on top. But in mathematical modeling, we still have to find a connection to the real world. So we need an interpretation of probability. So historically, you will find that there are 3 interpretations. The first one, I think, is the natural one. So you have a frequency interpretation. So if you make observations in the real world and something, you know, has a higher frequency, then you interpret that that it has also a higher probability. A very important deviation from that is that, you know, you have probability as a kind of belief. So this introduces the observer, so the frequency interpretation. Sometimes, if you look at it abstractly, like in Newtonian mechanics, you have no need for an observer, but for the Bayesian statistics, which is based on the probability interpretation of belief, this introduces an observer. Of course, it can also be a machine, but belief is something that is connected with some experience you had before the observation, which already gives you a kind of belief or kind of expectation of what this probability will, interpretation of what the probability will be at a certain time. And then the third interpretation of probability is the one I mentioned before. So this is the abstract view. You just define an axiom system for probability, and you don't interpret it any further, as long as you do just mathematics. This is also, as I said before, a very fruitful way, and it was a major milestone in the development of a proper probability theory, which of course was around already for centuries and was used, for example, by people like Pascal to understand certain games people were playing, for example, card games. But it was actually Kolmogorov that introduced the so-called Kolmogorov axioms, and only then did really probability theory start to thrive. So we have really to discuss the Kolmogorov axioms because they are so fundamental to probability theory. Now, what are the axioms? So for any probability P of A, where of course A must be as an element in this sigma algebra curly A, we have to assume the following. So A1, the probability of any event A has to be larger or equal to 0. Yeah, so because we, how we define probability, if we go to 0, the interpretation is that the probability has vanished, so there is no chance something can happen if it has probability 0. On the other hand, if it's larger than 0, then this event you are measuring is becoming more and more likely. So we have to go to A2. The probability of any event to take place within, the whole sampling space omega must be 1. So we have to observe something for sure, otherwise our probability would not be defined properly. And the event that is associated with looking at the whole sampling space omega, this is called A omega, and of course this is equal to omega. Now, if we have several subsets, so several elements in the sigma algebra curly A, then the question is, of course, what is the probability if we look at all these events separately? So first of all, it only makes sense to define this if all these elements in A are disjoint sets. But then if you have that, then if you look now at the probability that you look at the union of all these events, then this means you can compute the probabilities independently, and then the whole probability of this union is just given by the sum of each probabilities independently. Yeah, now we are slowly coming towards dynamic models, and for that you will see that you have to introduce random variables, so let's discuss them. A random variable will be something that starts from our sampling space omega, but then will map into another space which we call xi. And yeah, so why the question, of course, then, is that if we define a random variable as a mapping from the sampling space omega to some other space xi, what is the interpretation? Well, the interpretation usually is that you have a so-called reduction of observational depth. The idea is, of course, that omega is a very, very large sampling space. So, it can be a laboratory. For other experiments, it can be the whole world. For even other experiments, it can be the whole universe that is represented by omega. So that is a very large space, but we only, for example, are interested in an experiment in certain events that, for example, also have a certain numerical value. And this is exactly why we introduce that space xi. So one should also say that the random variable then is, of course, carrying over the randomness in omega that is described by the definition of the probability on omega. It carries this, of course, over to this space xi. Yeah, so let's make this connection between the sample space omega and the space xi a little bit more profound. And for this we will go back to our black box model we have discussed in lecture 1. So if you don't remember, you can go back to the slides in lecture 1. And yeah, let's look at an illustration of that. So if we associate our black box, so everything that has certain, now of course random mechanisms, then you have here the black box associated to omega, and now the random variable x, you could actually write this in this way. You write x is a mapping from omega to xi. Then you see the interpretation of xi here is that this extracts certain numerical values out of omega. So for example, you measure with a random variable something like the temperature in omega, and then you see that this would be measured continuously and would give rise over time here to some observation which lives in this space xi. Of course, today we will not look at continuous observations, but we will only be interested in discrete events. In this case, xi, for example, would just be something like the natural numbers n. So yeah, in our examples today, this will be just given by n. And why? Well, it's because we will just count events. So in this case, yeah, we will have look. We make one. So these all will be events over time, which can be observed individually, and then we will have an outcome like that. And yeah, n will just then measure the number of events we have after a certain time, which would then be over a period of time. Okay, so let's go a little bit further into the definitions. So a random variable pre-image is given by the mapping x to the power -1, so the inverse mapping. Well, not the inverse mapping, sorry, the pre-image mapping. So this is defined by all omega in the sampling space such that the random variable applied to such an element of omega is exactly some observation x, which lives in the in the numerical observation, or let's call it observation space capital Xi. This is called then the pre-image of the single element set x in this observation space Xi. More general, the pre-image of a whole subset of the sampling space omega. So we look at we look here at all omega in omega such that the outcome of the random variable is exactly in the subset B of Xi. This is called the X pre-image of the set B. So it's very interesting to observe that the pre-image construction defines a mapping, an inverse mapping from the power set P of Xi to the power set of the sampling space P omega. Now if the mapping, the random variable x from omega to Xi is invertible with the inverse mapping Ix, which is then of course a mapping from the observation space Xi to the sampling space omega, and it holds that this pre-image of some value of x in Xi is exactly, which is exactly defined as the omega in omega, such that the random variable applied to omega is equal to this numerical value x. Then this is exactly this kind of inverse mapping I of x, which we have looked at before. And this then holds, of course, for all x in the observation space capital Xi. But in contrast to the inverse mapping I, capital I, x, the inverse mapping which is defined on the power sets of psi and omega, always exists. Okay, now we come to the stochastic process. Yeah, consider a random experiment with a sample space omega. A real valued random variable x is a function that assigns a real value to each outcome in omega. So we have the random variable is a mapping from an event A to R, just to R, to the real numbers. Here we interpret omega not only as the sampling space but also as the state of the system. So this is important. So in part 2 of this lecture series, we will of course look at states of the system, and with the idea that the state then is depending on time. So we define some process that will change the state of the system. Now a stochastic process will be a collection of random variables that are now parameterized by a set we call time. So we introduce time now. Look at the definition of the stochastic process now. A stochastic process is now a random variable, parameterized by the time set, so xt. So this is the set of all random variables depending on t, such that t is an element in this time set. This is therefore a collection of random variables where for each t the index set capital T, the time, is defined, and xt is then a random variable. And any realization of the stochastic processes of this stochastic process x of t is called a sampling path. Of course, you might think of, why have I written down this so complicated, why do I introduce here a time set t? Well, this is very convenient because sometimes we have discrete time only in order to define a kind of dynamic process. So in this case t would something like be something like the integer set. If you go into negative times and positive times, so you go into the history and into the future. But most often our time will of course be the real numbers. So the real numbers of course have a linear order, so that's important for us in everything we discuss here in this lecture, that you have an order of time points. So you can say a time point t1 is later than a time point t2, for example. But of course, for example, if you go into relativity theory and its extensions, and also other interesting theories in physics, but also potentially in other applications, the time set could even be the complex numbers, and then you lose your linear order of time. So events then can also be only partially ordered. That means you cannot decide which time point is before or after another time point. So that can be nice if you know exactly when you are dying. Maybe in other theory you don't know exactly when you are dying in such a complex time frame. Right, so let's go to now a much simpler kind of a stochastic process. As I already said before, we are now looking only at discrete events from now on, and therefore we are looking at counting process. Our time index set now will just be the real numbers. So we are looking at continuous time, but in continuous time we are looking at certain time points when something is happening, and that is something we call an event. Okay, so let's define a counting process. A counting process is a stochastic process, but now instead of xt we call it nt, just to say that this is integer valued. So we have n is depending continuously on time, and t is supposed to be bigger or equal to 0 without loss of generality. And this is said to be a counting process if n of t represents the total number of events that have occurred up to a time t. Hence, a counting process must satisfy 4 axioms. So the first of all is that if we count events, this means n of t has to be bigger or equal to 0. So what that means is either we count no events or we count some events, and then this is bigger than 0. Then n of t is integer valued. That is also clear because we count. And if a time s is less than a time t, then n of s is less or equal than n of t. That is also clear. That's what we expect from a counting process, because if we have more time, we can count more events. Now let's look at axiom 4. For any time s less than a time t, the difference between n of t and n of s equals the number of events that have occurred in the interval st. This is also, of course, making naturally sense. Okay, so a counting process nt from a sampling space omega to n for all t and t, and remember our time here is real valued, so it's continuous time, is a special simple stochastic process based on real valued random variables. The sampling space omega can represent anything in the real world where we, within its system boundary, can observe any kind of event. The counting process then just keeps track of the number of events that we count and really nothing else. So you can only, if you have a counting process, you can only observe an event, but you could, for example, not say what kind of event that was. For example, whether a certain atom did decay or something like that. We don't observe. We just observe the decay itself and count it. Okay, very important for the characterization of these counting processes is the idea of independent increments. So a counting process is said to possess independent increments if the number of events that occur in disjoint time intervals are statistically independent. What is the idea about that? Well, it means, if we shift a certain time frame of time, so a certain interval of time over the process, then the number of things we observe should be statistically independent of each other. Look, this in contrast to the definition of stationary increments. So a counting process is said to possess stationary increments if the distribution of the number of events that occur depends only on the length of the time interval of observation. So if you shift the time window again, but you keep the same length of the time window, then you should actually observe similar numbers of events. So what we can say equivalently is that for some time s larger than 0 and some time t2 larger than t1, the random variable, which is defined by the difference of n of t2 plus s and t1 plus s in the interval that is now going from a time t1 plus s and a time up to a time t2 plus s, must have the same distribution as the number of events n of t2 minus n of t1. So s is used to define the length of this shifting time window. So, and that must be inside the interval t1, t2. Okay, so I think you understand what stationary increments are. And with this we define now the most important counting process of them all, and we will use this as a reference throughout the lecture, and that is the Poisson process. Yeah, and I will give you two definitions of the Poisson process, and then I will give you a theorem that states that these two Poisson processes are equivalent. So let's go to the first definition, which we call capital A. The counting process n of t, which is the set of all n of t such that t is positive in time, is called a Poisson process with rate lambda a positive rate if and only if 1. So we have that at the beginning we count nothing, so we start with 0 events. Now 2 n of t has independent increments according to our definition, and 3, the number of events in any interval from 0 to t of length t, is Poisson distributed with mean lambda t. That means for all times st which are positive, we have that the probability that the difference between the counting process at time t plus s and the process at time s is exactly n, and this is given by the Poisson distribution, so this should be e to the power lambda t times lambda t to the power n divided by n factorial, and this must hold for all numbers of events n from 0, 1, 2 and so on. In order to define now the Poisson process again in a different way, we have to define the rate of convergence. But before I do that, let me just say that for the ones of you who know what an expectation is, then the expectation of the counting process up to time t will just be given. So the expectation to have n of t numbers of events, that will be exactly given by lambda times t. And this is of course explaining why lambda is called the rate of the Poisson process. Okay, but now let me give you the definition of the order of convergence. Maybe you know this actually from numerical analysis. I hope so, at least it should. It's a very important definition there. So a function f, which is a mapping from R to R, is said to converge of first order in h positive, if the limit for h going to 0 of f of h divided by h is actually equal to 0. So we say in this case that f converges as little o of h. Now let me give you the second definition of the Poisson process. So what do we have here? The counting process n of t, as we find before, is called again a Poisson process with rate lambda positive, if and only if we have 4 different characterizations, 4 axioms. The first one is the same as before, so if we start at time 0, we have not observed anything yet. If the second one is that n of t has stationary and independent increments. Very important, but now 3 is defined a little bit different. We assume that the probability that we count in a little time, which is given by h, exactly 1 event, is given by the rate lambda times the length of this little time interval h plus little o of h. And we have a last axiom 4, and this says that the probability that if we look at a very, very small time interval, which is given by length h, that, and if we, the probability that if h is very small and we observe actually more than 2 events, so that this is bigger or equal to 2, this is also given by little o of h. Now we come to the equivalence theorem, and that states, that's easy to state. So it just says the 2 definitions of the Poisson process given in these 2 definitions, A and capital B, are equivalent. Now the proof of this is very interesting because it also introduces a lot of techniques which we like to have in the course. So I will now go through the proof of this, but in a very rushed way. Just want to give a few comments. What I really would like you to do is to go through this proof yourself. I will also give only one direction of proof. Of course, the equivalence of these 2 definitions means that A has to imply B and B has to imply A. I will only give you one direction where B implies A. So the idea is that we define these probabilities which we call P subindex n of t, and this is exactly defined as the probability that the counting process has exactly at time t counted n events already. T, of course, is a positive time. Now, and the idea is that we derive an ordinary differential equation for these different quantities Pn of t, and we start to derive an ODE for just P0 of t. So that is the probability that at time t we have still not counted any event. So the idea is that we derive a difference quotient in that way, and you should be able to see that 2 holds, so that this difference quotient is given by this formula. And then, of course, we go to higher event counting, so we look at Pn of t now. We have the same idea again to construct a difference quotient. So we have to look, we have to get a formula for Pn t of h, of course. Then we construct the difference quotient in this way. We use the axioms. We can use all axioms in the definition capital B of the Poisson process, and this gives us a differential equation for Pnt. And then we first look at the solution for P1t, so the process where we exactly count one event, and using this formula then we use the idea of induction. So we think we know everything for the process Pn minus 1, where we count n minus 1 events, and then we derive a formula from that, from this for Pn of t, and that's more or less the proof in one direction. So please also try to prove this in the other direction. You have the slides of this lecture, so this is something you really should be able to understand. Let's finish this lecture with the conclusions as always. So we had now a first encounter with probability theory. You know what the Kolmogorov axioms are. It's very important. It's really something you should know by heart. all the time. Then you have seen that it's very important if we introduce now dynamic processes, we really have to look at random variables, because then a stochastic process will be random variables that are parameterized by a time set. And we discussed today in detail the so-called counting processes, which are very important because also in future we will be counting discrete events in systems. We do this for a very long time, and actually even the differential equations in the end will be counting discrete events like collision events, where, for example, atoms bump into each other to form molecules. And the only difference to counting events will be that these processes then later will be assumed to happen very, very, very often, so that you can talk about rates and you can define differential equations. So it's very important to understand counting process first. And yeah, this concludes the lecture for today.